Anyhow, I got back at him.
How'd you get back at him?
How was your revenge? I don't know how many years it was. I mean, maybe 20 years after he was out, he came back to the Shamrock Auction with his wife.
You
Before, you remember me? Oh yeah, I remember you. And his wife was like, "Oh, you do?" And I said, "Yeah, let me tell you why." And I told the story, and she was mortified because.
Wait, what's his name?
Just me. All right, we're on number 3. Number 3. Find the limit of the following sequences. All right, we're going to find the limit of these sequences. So I want you to look at what's going on and tell me where these terms are headed. What is going to be like their wall that they can't go past?
0.
0. So the limit of the first one is 0. Will those terms ever get negative? But they are going to continue to get smaller. So therefore the limit is 0. All right, what about number 2? Now, in number 2, I kind of given you a little like formula. So what we're really trying to do is find the limit as n gets really, really big of this set of numbers, where the numerator is 1 bigger than the denominator, basically. George? It is, George. And everybody in the room should know that, because at the very beginning of the year, and again in chapter 7, we graphed things like this. And the limit is the horizontal asymptote. And where's the horizontal asymptote? 1. The limit is the horizontal asymptote. So if you know how to find the horizontal asymptote, you can find the limit. What about C? There's no limit. What's happening to these terms? They're just getting bigger and bigger and bigger. So this sequence is what we call divergent. The word divergent means there's no limit. It's exploding. How about D? What's the limit there? That one has no limit either, because every term of the sequence is either 1 or -1. You can't have 2 limits, okay? You can't have 2, you have 1. And all this thing is doing is flip-flopping back and forth, so this one is also divergent. However, it's divergent in a different way than C is. Would you agree with me? Yeah. In C, the terms are heading toward positive infinity. So if I were to graph it, it would be, right? D, they're just flip-flopping back and forth. They're not growing or shrinking, they're just going back and forth. All right, E, the limit is? 3. F?
0.
0. Why is it 0? You got the big power on the bottom, so you have no n cubes on top, right? Just like the horizontal asymptote. How about G? Divergent. No limit. When we did this before, when we were graphing, you said no horizontal asymptote, right? Connect the dots here. It's the same thing we did before. H?
0.
Now there is a limit for this one. What is it? Think about it. What are the terms doing? What's the first term? The first term would be 2/3. What's the second term? 4/9. What's the third term? 8/27. What are you doing, guys? You're multiplying by 2/3? What happens when you multiply something by 2/3? It gets smaller. Now, is it ever going to be negative? No, but it's going to keep on getting smaller and smaller and smaller. Now, I, that one has no limit. That one's exploding, because what are we doing? We're multiplying it by 1.5. And every time you multiply something by 1.5, doesn't it get bigger? How about a nod? Yeah. Okay, now J, do not be confused. What's the limit of the first piece in J? 4. What's the limit of the second piece in J? 1/2. 4 plus 1/2 is 9/2, 4.5. So the limit of a sum is the sum of the limits. Just find the limit of each piece and add them together. Or if you wanted, could you get a common denominator and add those two and make one term? Yeah, and get the limit that way, but it's easier just to do them individually. Same thing with k. What's the limit of the first piece? 4. Limit, oh, they're the same thing. Limit of the second piece is a half, so the limit of the product is 2. All right, L. Second piece of that's no issue. What's the limit of the second piece? 2/3. What do you think the limit of 3 is?
1.
3. The limit of a constant is itself. Is it ever going to go past 3? Nope, the limit of a constant is the constant. So that one would be 3 plus 2/3. And how about M?
4 minus 5/3.
Watch it. 4 minus 0. What's the limit of the second part?
Oh.
0. There's no n squared on the top, so that one would just be 4. Okay? Before lunch, we talked about arithmetic sequences. Arithmetic sequences can be generated. You can find terms, find information using this formula. You are not responsible for memorizing the formula, but you do need to know that that formula goes with arithmetic sequences. Okay? So I'm going to give you a list of formulas, some are arithmetic, some are geometric, and you got to know which one goes with which. This is your arithmetic formula to find a term. So this means the nth term. The nth term. So like a sub 3, we talked about this yesterday, I think, means the third term. This means the first term. This is the common difference. Remember what makes a sequence arithmetic? We get from term to term by adding the same number. That number is called the common difference. So that's the number that you're adding to generate your sequence. And then n minus 1 is, well, if I were finding the third term, that's n. So n minus 1 would be 2. This is what we call an explicit formula. This will find any term you want. So 4a says, here's my sequence. Find the explicit formula for this sequence. Now, we're in the arithmetic section, so you're guessing this is arithmetic, but can you, if you just found this laying out in the hallway, would you recognize it as arithmetic? Yes, because we're getting from term to term by adding 4. So D is 4. Now, this is your explicit formula, so we're building it specific to this problem. What's my first term? Negative 6. We just decided our difference was 4. Remember, an explicit formula is going to find whatever term you want. So if you wanted the 100th term, this will do it. Now, I do expect you to clean that up a little bit. So we'll do a little distributive here. And what do we end up with then is our explicit formula, a sub n equals either negative 10 plus 4n or 4n minus 10. It doesn't matter what order you write it in. Okay? Find a sub 24. That's easy. A sub 24 is going to be 4 times 24. This n is this n. They are the same thing. So a sub 24 is 4 times 24 minus 10. What is that? 86?
86.
Okay? Now, recursive. I want you to go back to to the sequence itself. And if I said, Julia, tell me the next term, you probably wouldn't mess with a formula. What would you do to find the next term? I would add 4. So what Julia just did was tell me how this sequence progresses recursively. What it means to be recursive is start with a given term. So 1, 2, 3, 4, 5. Julia started with the 5th term, added, 4 to it, and what did she get? What would she get? If she took the 5th term and added 4, she would get the 6th term. And if we wanted the 24th term, recursively, the 24th term would be the 23rd term plus 4. Now, that's a pain in the butt, because why? You don't know the 23rd, and how do you get the 23rd? Well, you gotta know the 22nd. How do you? So this is one where you'd have to build the whole thing. It's much easier to do your explicit formula. What does this look like in terms of a formula? Julia told us how it works, and that's exactly how it works. So I'm gonna put n's in now, okay? Instead of numbers, I'm gonna use n's. So if I put an n here, what would this base have to be here? This is n plus 1. That is the recursive formula. It says, give me a term, I'm gonna add 4 to it and get the next term. Now I can't do this unless you tell me what the first term is. Because if you're gonna build recursively, does it make sense to you? You have to have a starting. Then you can go. Take this term and add 4, add another 4, add another 4, keep adding 4, that's fine, but you have to know where to start. All right, D. Now we're making it interesting. We have ln3, ln6, ln12, This is supposed to be arithmetic. What's 6? 6 is 3 times 2. When I have the logarithm of a product, I can pull that apart. And when I pull it apart, what does it become? Hey, remember our properties of ln? Exactly. So this is going to be ln3 plus ln2. Remember, when the logarithms are added, the numbers are multiplied. That's one of your main basic properties of logarithms. Okay, what about this one? What's this one now? This is going to be, it's going to be 3 times 2 times 2. So it's going to be ln3 plus 2 ln2's. Is that okay with you? 4 ln2 plus ln2. So without doing any more, what appears to be being added here? ln2. So the nth term is going to be the first term, which is ln3, plus the common difference, which is ln2, times n minus 1. Right? Let's distribute and see if there's anything we can do to clean this up. This is going to be n ln2 minus ln2. If I distribute, is that what I've got? Now, can these two combine? What happens when I have a log minus a log? They go together as a division. So this is going to be ln either 3/2 or 1.5, whatever you're comfortable with, plus n ln2. And that's going to be your nth term. That is your explicit formula. So this problem always catches people off guard because it looks like we are multiplying but we're really not, because in logarithm land, when you multiply, you're really adding. What's a sub 10? Here's my formula, what's a sub 10?
Natural log of 3 halves plus 10 times natural log of 2.
Now, this isn't a lesson in logarithms, but it is good practice for us. What do I do with a number out in front of a logarithm here? Where does he end up? Exponent. So I have ln 1.5 plus ln, what's 2 to the 10th? I should know that, but I forgot. It's 2 to the 10th. 1024. Now these guys are being added, so I'm going to combine them as a multiplication. So 1536. So if I kept going here with my sequence, the 10th term in the list would be ln 1536. Alright, now what about a recursive formula? So ln3, ln6, ln12. Julie, you did such a great job. I'm coming back to you. If I said, here we go, this is what we've got so far. What's that 5th term going to be? What would you tell me that 5th term was? Don't look at all this junk. None of this junk. No, just look at, here, just use your common sense. What do you think this number is going to be? ln 48? How did you get that? Well, yeah, this was gonna be a lot harder to do, because what you did was you took that number and times it by 2, but you didn't take the whole term times 2, you only took the number times 2. I don't know, I gotta think about that for a second. How am I gonna, I took my 4th term.
33 times 2n.
Why couldn't you just do plus natural log of 2?
Well, you can, absolutely you can do that. You can do that. So yeah, that's a good idea, Maren. So a sub 5 is a sub 4 plus a natural log, another ln2. So this was our 4th term, and when we added that, we ended up with what she got. So we took our 4th term and added an extra ln2. So how can we generalize that to the nth term? What will a sub n plus 1 be?
Equals a.
Our nth term plus an ln2? Yeah, that's what we're doing. And then add what your first term was. What was our first term? Gotta have a starting point. If you're gonna build this recursively, you gotta have a starting point. All right, you can see the next thing there on the paper is our geometric formula. What do you think the R stands for? The ratio, which is the number that we multiply by. So for problem A, what is our, this is your explicit formula. What is our explicit formula gonna look like for problem A? A sub n equals, what's my first term? 3. What am I multiplying by? 2 to the n minus 1. And then it says, find the 10th term. So what will the 10th term be? 3 times 2 to the 9. These things get big really fast. Oh, that's 1536 again. So that would be the 10th term in the sequence. All right, I'm gonna stop here for a second because I wanna share something with you. Got Tess sitting back there. Tess's aunt was a student early in my career, so was her mom actually, and she's very smart. And she came in one day, I had her in second year algebra. She came in one day and said, Miss Ford, they said something on TV. My dad and I were watching TV, and he was very smart too. They're all very smart. And she said, this is what they said. It can't be right. My dad said we could talk about it. And I said, okay. And she said, they said on TV that if you take a standard checkerboard, like a chess, 8 by 8, you know what I'm talking about? And you put 1 checker on the first one, 2 on the second one, 4 on the next one, 8 on the next one, 16 on the next one, and so on. By the time you get to the last square of the checkerboard, so the 64th square, there would be enough checkers stacked up to reach the nearest star. I'll never forget her saying, even if you count the sun, that's 93 million miles away. This just doesn't seem right. Well, we can prove that statement because isn't that geometric? Our formula says that the 64th term will be the first term times the ratio to the 63rd. Well, if you type that in on your calculator, that's a mighty big number. But remember, that number represents how many checkers you have stacked. So I'm just gonna randomly divide it by 3. Maybe I can get 3 checkers in an inch, I don't know. I'm just gonna say 3 checkers stacked on top of each other in an inch. And then divide it by 12. And divide it by 5,280. This is 4.85 times 10 to the 13th miles worth of checkers. Isn't that amazing? That ties in directly with when we graphed exponentials. Remember when we graphed exponentials? What happened here? Really, really big, really, really fast, right? Yep. All right, we'll pick up there next time. Have a great day.
That is wild. We should do that. Just kidding. Yeah, we can't do that. I like how we do that. That is the thing. No, that's right.
No, can't be before except on Monday, Wednesday, and Friday.